This is Module 11, IPv4 addressing of the Cisco Networking Academy Introduction to Network 7.0 curriculum. Of all the things in this first course of the Cisco Academy, it is my opinion that IPv4 address structure and how to address networks is probably the most critical part of the entire course. If your addressing structure is not correct and efficient, your network will not function. First, we will go through the address structure of an IPv4 address. An IPv4 address is made up of 32 bits. It is a hierarchical address, and you have two portions, a network portion and a host portion. The network portion is used to get packet from one network to another, just like in the postal service. The postman does not care about the final recipient. They care about getting it to the residence of that recipient. So when we are directing a packet through a network, we are only concerned about the network. The host portion does not come into play until it reaches the final network, and then the host portion directs it to the individual host. When determining the network portion versus the host portion, you must look at the entire 32-bit stream. A subnet mask is used to determine the network and host portions. As we can see here, the network portion is the 192.168.10, while the 10 is the individual host on that network. To identify the network portion of an IP address, we combine it with a subnet mask. We do a logical AND function. An AND gate has a symbol like this. It can have two inputs or more inputs, but it must have at least two. The inputs are normally labeled with the lower letters of the alphabet, while the output is labeled with the higher. The logic function of an AND gate if we took all possible binary values, 00, 01, 10, and 11, and put those into the AND gate, the output would only be high when all of the inputs are high. This type of logic you use every day. When you turn on a light, the light doesn't go on unless the switch is on and the circuit breaker is on and the main breaker is on and all the way back to the electrical grid. They all have to be on before the light bulb will light. The same logic applies here, that all the inputs must be high in order to get a high out. When we combine the subnet mask with an IPv4 address, wherever we have a high, the number in the network or in the IPv4 address stays. Whenever the subnet mask has a low, it wipes out the numbers in the IPv4 address. So for the network portion, the subnet mask is all highs. For the host portion, because we want to eliminate that, the subnet mask is all lows. A subnet mask is always a series of ones coming in from the left. The host portion is always a series of zeros coming in from the right. Where the transition goes from 1 to 0, that determines the network portion to the left, the host portion to the right. The prefix length is a less cumbersome method used to identify a subnet mask address. Prefix length is always used in IPv6. The prefix length is the number of bits set to a 1 in the subnet mask coming from the left. Remember, you never have a combination of ones and zeros. It is always solid ones coming from the left, solid zeros coming from the right. We use a slash notation or prefix length to indicate how many consecutive ones are in the subnet mask. Such as in this example, a /8 would have the first octet all ones, while the last 3 octets would be all zeros. So only the first octet is network. The last 3 octets are host. If we take a look at another example, such as the /26, you have 3 groups of 8 that are all ones. 3 times 8 is 24, plus 2 additional bits, filling it out to a /26. If we convert these numbers to binary, we would see that we could have a 0, we could have a 128, a 192, a 224, a 240, a 248, and a 252. We may also have a 254 or a 255, but those cannot occur in the very last octet. The reason that they cannot occur is that if I only left 1 bit to be a host, it could either be a 0 or a 1. A 0 being the network address and the 1 being the broadcast. It leaves no room for an individual host. The logical AND Boolean expression is used in determining the network address. An AND gate, along with a combination of other gates, is referred to as Boolean algebra, and it is named after Dr. George Boole, who was the first professor of mathematics at the University College in Cork, Ireland. And Boolean algebra, although we may think of it as being a modern type of algebra, was actually developed in the 1600s. The logic is the same whether we are working with networking or electronics or mechanical. It is still the same. As I explained earlier, in an AND function, a 1 and a 1 will give us a 1. A 1 and a 0 is a 0. A 0 and 1 is 0. Any 0 in is equal to a 0 out. The only time that you have a high is when all the inputs are high. And I use the term all because in our case, there's only 2 inputs. But you may run eventually into a case where there are more than 2 inputs. And all would have to be high before you get a high out. So to identify the network address, the IPv4 address is logically ANDed bit by bit with the subnet mask to identify the network address. Think of somebody who paints cars. If they don't want paint on a particular part, they mask it off with paper. We are doing that for the network portion so that we keep the network portion. And we are allowing the host portion to be painted over and become all zeros. Within each group or network, we have 3 main types of addresses. When the host portion is all zeros, that is referred to as the network address, or sometimes referred to as the wire address. When the host portion is all ones, that is a broadcast address. Neither the network address nor the broadcast address could be assigned to a host. If we were to look at the chart, all zeros is the network. All ones is the broadcast. And between those two ranges, 0, 0, 0, 0, 0, 0, 0, 1 to 1, 1, 1, 1, 1, 1, 1, 0, these are the range of host addresses that we could assign to host computers, printers, or other devices. One point to mention here is that when we subnet, we always lose 2 addresses, one for the network and one for the broadcast. So if I were to take a network and divide it, I would now have 2 network addresses, 2 broadcast addresses. So as I subdivide or subnet my network, I lose addresses. But the benefits of subnetting outweigh the loss of addresses. As mentioned in other parts of this curriculum, we have 3 types of messaging. First is a unicast, and it goes from one host to one destination, 1 to 1. This is the most common. We also have broadcast, such as when A computer turns on, a host will turn on, and it needs to find a DHCP server. It sends a broadcast that goes to every other host in the network. Once that host responds, then it turns into a unicast that the two can connect with one another directly without sending a broadcast out. Because the broadcast goes to everybody, the more broadcast messages that there are, the less bandwidth is available for the transmission of data. So it makes the network more inefficient when there is an increasing number of broadcasts. Multicast is one source, and it is always one source, that goes out to everyone, but only the devices that specifically want to listen to that multicast will tune in, to use a phrase from television, to that particular multicast. Multicast can be many things. You may think of a multicast as streaming video. Just like at home, when you tune into your cable box to watch a particular show, it is like a host computer listening for a particular IP address. If I am sending out video to a number of hosts, as in this case on the right, I may be sending video out to 2 hosts. We would not send individual streams. We would send one stream, and the hosts that want to listen to the video can tune into that. We also use this to message between routing protocols and many other devices in a network. In IPv4, we have many types of addresses. First, because we were running out of addresses and IPv6 had not been fully implemented, we had to come up with a way to save addressing. One of the things that was developed was developing private addressing. This has been defined under RFC 1918, which defines both the public and private addressing. Anyone can use private addressing, but it is not allowed on the internet. You may check the address of your home computer. More than likely, you'll find that the address that you have received from your router is in the 192.168 range. This is private addressing. Private addressing, or addresses, are common blocks of addresses used by most organizations to assign IPv4 addresses to internal hosts. Private IPv4 addresses are not unique and can be used internally within any network, but they are not globally routable. The 3 groups of private addressing is the 10 network with a /8 as a subnet mask. This, as we will see in a later slide, is a Class A address. because it's a /8 separating the network from the host, only the 10 is the network. You have 3 octets, 24 bits for host. So this has the fewest networks and the most hosts. One that will fall into a Class B address is the 172.16, and that is with a /12 subnet mask. With the /12, it allows us the 172.16 through the 172.31. This has about an equal amount of hosts versus networks. The last is the 192.168. This is with a /16. This is in the Class C range, and here we normally have the largest amount of networks, but each network has the fewest amount of hosts. So we go from few networks, large amounts of hosts, to large amounts of networks, few amount of hosts. Because private addressing is not allowed onto the internet, it is not globally routable, we had to develop network address translation. And this will translate a private internal address to a public address so that it can be routable over the internet. A single address, when we combine network address translation with port address translation, in theory, could take 65,536 internal addresses and send them out using only one external address. This is a massive amount and does not work all that well. A realistic number to use when we combine network address translation along with port address translation is approximately 5,000 internal hosts could use one external address without much of a degradation in speed. When I say 5,000, if a computer has more than one web page open, each web page would count as one of the individuals in the 5,000 count. So it may not be a total of 5,000 hosts, but 5,000 open sessions. NAT is typically enabled on the edge router connecting to the internet, and it translates the internal private to a public global IP address. The configuration of NAT is covered in a later course. Within the address structure, we also have loopback addresses. We use these to test the protocol stack in our hosts to make sure that the operating system can work with the network interface card so that we have access out. To test this, we can ping the 127 network, such as 127.0.0.1. All of the 127s are loopback addresses. Normally, we only use 127.0.0.1. We also have a link local address. You'll see this much more in IPv6. A link local address begins with 169.254. You may have noticed if your computer does not have a network connection, the network card will be assigned a link local address in this 169.254 range. It is commonly known as automatic private IP addressing, or APIPA, or self-assigned addresses. It is used by Windows DHCP clients to self-configure when there are no DHCP servers available. In the address structure, we have different classes of addresses. The only ones that can be assigned to a host computer are A, B, and C addresses. If we were to look at the very first octet, the octet that is furthest to the left, Class A addresses begin with a 0, and the rest of the digits, we do not care what they are. So it allows us addresses from 0 to 127 in the first octet. Class A's, a default subnet mask is a /8. So A's have the fewest networks, but the largest amount of hosts per network. These are normally assigned to large corporations, service providers, and countries. A Class B goes from 128 to 191. A Class B address starts with 1, 0. And the rest of the first octet can be anything. So it always starts with 1, 0, and then could go from 1, 0, 1, 1, 1, 1, 1, 1, all the way down to 1, 0, 0, 0, 0, 0, 0, 0. This gives us a range of 128 through 191. A Class C always starts with 1, 1, 0. And the additional 5 bits, again, could be anything. And it allows us to go from 192 to 223 in the first octet, the most significant octet. A default mask is a /24. You'll notice that the masks shown here as a prefix length start with a Class A at a /8, which would be 255.0.0.0. Class B's at a /16 start with 255.255.0.0. A Class C would range from 255.255.0. So as you can see, Class A's have the fewest network, the most hosts. Class B's have about equal. Class C's have a tremendous amount of networks, but the fewest hosts per network. A Class D is a multicast address. Multicast addresses are used for many things. As discussed previously, it could be streaming video. We use the 224.0.0.5 and 6 for the routing protocol OSPF to communicate between routers. There is no subnet mask for a Class D. It is a strict number. It is not a network. Class E addresses, or before going on to Class E, Class Ds start with 1110. Class E's start with 1111. Class E's are experimental, and these are used by companies and developers when developing new products. Now, because these are all what we refer to as classful, as they fall into particular classes, it wastes a tremendous amount of addresses. You may have a small company that does not need a lot of addresses, but if we went with classful addressing, the lowest we could go would be a Class C, giving them 254 usable addresses, many of which would be wasted. Because of this waste, besides network address translation, we also started to use variable length subnetting and other types to make our networks more efficient. As we will see later, we will use classless addressing. Addresses are assigned first by the Internet Assigned Numbers Authority, IANA. They manage addresses worldwide. A company wishing to get an address assigned to them would contact their local authority. In North America, it's ARIN, the Assigned Registry for Internet Numbers. In South America, it would be LACNIC. The African continent would be AFRINIC. Asia, APNIC, and Europe, including Greenland, would be RIPE. IANA assigns groups of addresses to these organizations. It is then their responsibility to assign these when a request comes in. The individual authorities are referred to as Regional Internet Registries, or RIRs, and they are responsible for allocating the IP addresses to ISPs who provide IPv4 address blocks to smaller ISPs and organizations. Now, a network has different types of domains. First, there is a broadcast domain. When a host sends out a broadcast, such as a request to find a DHCP server, it goes to all the devices within the broadcast domain. The broadcast domain ends at the router. A router will not forward a general broadcast. If in the event, such as DHCP, the DHCP server is on another network, the router will be programmed to change the generalized broadcast to a directed unicast going to the DHCP server. A switch will not block a broadcast, so broadcasts go directly through a switch to every host and everyone connected to that network. You can imagine what would happen if a router did not stop a broadcast. How many host computers worldwide are turning on at this instant in time requesting a DHCP address? If that broadcast were to go to everyone in the world, no one would ever be able to get onto the internet or exchange data. So the only device that will stop a broadcast is a router. A layer 3 switch, because it does routing, can also stop a broadcast. The routers will not propagate the broadcast, and each router interface connects to a broadcast domain, and broadcasts are only propagated within that specific domain. So as we can see here in the diagram, the broadcast domain is everything within that box, and it ends at the router. Since the switches will forward a broadcast, they are all part or internal to the broadcast domain. The problems with a large broadcast domain is that these hosts can generate excessive broadcasts that negatively affect the network. Because a broadcast goes to everyone, other devices cannot be sending unicast messages until the broadcasts have stopped. So the solution is to reduce the size of the network to create smaller broadcast domains, and this is referred to as subnetting. If we divide the network address 172.16.0.0/16 into two subnets of 200 users each, we could use a /24 mask. So as you can see, we would have a 172.16.1 and a 172.16.2. We would be using the third octet to indicate which network or broadcast domain. So now I have reduced the size of my broadcast domain considerably. With 16 bits, the original 172.16 network could have 65,534 host computers. When I use the third octet to create two groups of users, each group, although we use 200 as a round number here, each group could be 254 users. So you can see the reduction in the number of hosts in the broadcast domain is considerable when we use one bit from the third octet to separate our groups. There are many reasons why we should segment our networks. It reduces the overall network traffic and improves network performance. We can then use it to implement security policies between subnets. It also reduces the number of devices affected by abnormal broadcast traffic. And some of the variety of reasons: location, group or function, or device type. Some of the things that you may think about is if you took a major car company, such as General Motors. They may segment their large network into a network for Chevrolet, a network for Cadillac, a network for GMC, a network for Delco. So they could subnet to give each group its own domain, which could also be further subnetted. When we assign addresses to device types, it is good practice to separate our device types. Here, they've separated their printers and their servers and their hosts. Even within a network where you may have a combination of hosts and printers and servers, it is always good practice to take your address block and determine where the servers are going to reside, where the printers are going to reside, and where hosts may reside. This gives you some logical structure to your network. To subnet an IPv4 network, we first look at where is the network bits versus the host bits. It is very easy to subnet at the boundaries of 8, 16, and 24. The longer the prefix length, the less individual hosts you have. So if we were to subnet on an octet boundary, taken for example the /16, we could use the third octet to indicate what subnet. So we could have 254, actually 254 networks, and each one having 254 hosts. And we would use the third octet to identify which network, such as 0 or 1 or 2. Each subnet, because now only the last octet would be available for hosts, each one of those subnets would have 254 hosts. Subnetting on a fixed boundary, such as this, can also be wasteful as far as addresses are concerned. Because here, each network would have 254 hosts. If I had a serial connection between two routers, this only needs 2 hosts, one address for each end. But we would be providing this network with 254. So we have just wasted 252 addresses. Here, in this example, they take a class A, the 10 network private addresses, with a /8. And they're using the second octet to indicate the network. So 10.0, 10.1, 10.2, 3, 4, 5, and so on. Now, because everything is fixed, each group has approximately 65,534 hosts in it. Here, they're going to use the third octet. So they're using the first octet to indicate a range or a host range, and then they further subnet it using the third octet. Now each group would have 254 possible hosts. And we would end up, because between the second and third octets there are 16 bits, we would have 65,536 possible subnets. The last subnet is normally not used because the broadcast for that is the broadcast for the entire group. Now, if we decide to use the host bits, you must remember that when you get an address from your service provider, the network is fixed in stone. You cannot change the network. You can only change your host bits. Here we are looking at the subnet mask, and the /25, we would have 8 for 255, 8 more, so I'm at 16. 8 more gives me 24, and 1. So it would be a 255, 255, 255, 128. Remember, as we discussed earlier, it is a solid stream of ones, followed by a solid stream of zeros, indicating the network portion and the host portion. In shorthand notation, you see the small n's. That's used for an individual bit. We could also write this combination as capital N, capital N, capital N for the 255, 255, 255, and then small n followed by 7 small h's, indicating the host bits. If an octet was all hosts, we could use a capital H. As you can see, as we subnet, here borrowing 1 bit, I get 2 subnets. Each one could have 126 hosts, because remember, you lose the network and the broadcast. If I borrowed 2 bits, I could have 4 possible combinations: 00, 01, 10, and 11. Each one could have 62. So you can see, as I borrow bits, the number of subnets increases, while the number of hosts per subnet decreases. So the subnets go up as I borrow more, the hosts go down. It is commonly asked, what is the rule to subnet a network? And there is no rule. It is whatever works for the business that you are subnetting for. Taking an example, Dunkin' Donuts versus Home Depot. There are many more Dunkin' Donuts than there are Home Depots. But the Dunkin' Donuts need much fewer addresses, whereas a Home Depot needs many more addresses for cash registers, computers, and other devices. But because there's not as many Home Depots, they need less networks. So Dunkin' Donuts needs larger numbers of network, a fewer number of hosts per network, while Home Depot needs fewer networks, but more hosts per network. So there is no fixed formula as to where to divide networks versus hosts. It's always to fit the business need. Now this is subnetting with a /16 and a /8 prefix. Here, with the /16 prefix, we are using the 3rd octet for our subnet. And the subnet comes over to the network portion. So as you can see, with the 1, that would give us 128. And we could either have a 0 or a 1 borrowed in that bit. That gives us 2 subnets. If we look at just the subnet bit, because we've borrowed 1, that could either be a 0 or a 1. The subnet mask just indicates that is part of the network portion. Here, I don't want you to think, oh, it always has to be a 1. No, the subnet is indicating what part is the network bit. As I borrow more bits, the number of subnets increases. Here, we'll consider a large enterprise that requires at least 100 subnets. In order to get 100 subnets, we use the powers of 2. The easiest way would be to use our powers of 2. 1, 2, 4, 8, 16, 32, 64, 128. Now, to get 100 subnets, I would need these bits because they would add up to 127, obviously giving me at least 100. So I'd have 1, 2, 3, 4, 5, 6, 7 bits. So if I wanted at least 100, if these were my host bits as indicated, I would take 7 from the left and designate those as my subnets. So this figure displays the number of subnets that can be created when borrowing bits from the third octet and the fourth octet. There are now up to 14 host bits that can be borrowed. You always have to leave the last 2. A good rule of thumb is to always borrow at least 2 and always leave at least 2. The reason that we say borrow at least 2 is that the last subnet normally cannot be used because the broadcast is the broadcast for the entire network. It can be broken down further so that we do not lose all those addresses. Here, we'll consider a small ISP that requires 1,000 subnets. In order to get 1,000, we must borrow 9 bits. You'll notice from the chart the powers of 2 going vertically, although they have left out the number 1. But as we can see, we have to go up through the 10 bits to get 1,024 combinations. If we were to look at that with the powers of 2, 1 would be included. So I would only need these bits. And if we count these up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bits in total. They're showing it in a little bit different structure. I find it much easier to use the powers of 2 that we use for converting numbers anyway. It means that from the host portion, coming in from the left again, we always borrow from the left. We will borrow the first 10 bits. The remaining bits are now all for host addresses. As I previously stated, we want the subnet to meet the requirements of the network, whether we need more hosts or we need more networks. So an intranet is a company's internal network, and that typically uses private IPv4. You may have the DMZ, and this is where a company may put their web servers for their publicly available website. When we deal with security, the inside network, the intranet here, has a value of 100. It is the most trusted. The DMZ has a value of 50. It is a little bit trusted. And the internet on the outside has a value of 0 because it is not trusted at all. And as a security practice, we can always go from a higher to a lower, but not the other way. The DMZ devices, they would have to be configured with a public address, or we would also use natting to give them a fixed address that the outside community on the internet could find. When we are planning our subnets, as we've talked about, we need to determine the number of hosts the subnets needs versus the number of networks that we need. So an analysis of our usage must be done. Now here, if we took a look in this network, corporate headquarters has been allocated a public network address of 172.16.0.0 with a /22. Now the /22 gives us 10 host bits. And with 10 host bits, we would have 1024 combinations. Because I lose the network and the broadcast, I would have a total of 1022 host addresses. So out of the original 1024, I am left with only 1022. There are 5 sites and 5 internet connections, which means the organization requires 10 subnets. And the largest subnet will require 40 addresses. Now, in order to get 10 subnets, again, if we look at the binary, 1, 2, 4, 8, 16. To get 10, I need 4 binary digits. So that I would cut out the first 4 of my host that's available to me to use to indicate the subnet. So now, instead of a /22, because I have borrowed those 4, it will now be a /26. So the subnet mask would be 255 255, 255, that's 24, and two more, 192. That leaves me with 1, 2, 3, 4, 5, 6 bits for the host. If we went out 6 bits, 1, 2, 3, 4, 5, 32, and then 64, six bits would give me 64 combinations, 62 I could actually use. So I would end up, in this case, with 16 subnets, each one being capable of 62 host addresses. Now, because these networks use or need different amounts, each one has been allocated 62 hosts. This one only needed 40, so I lost 22. This one needed only 25. So if I subtracted 25 from 62, that would give me 37. Lost. Here we needed 30, so we lost 32. Here I needed 10, so I lost 52. Here I needed 15, so I lost 47. And on each one of these, where I only have 2 connections, I would have lost 60. Well, 1, 2, 3, 4, 5 connections. So I would have lost another 300 addresses there. As you can see, if we were to add this up, that's a lot of addresses that I have wasted. This is using a single mask, a /26. This is saying that one size fits all. And anyone who has gone to the shoe store knows that one size does not fit all. So in order not to waste addresses, we have developed variable length subnet masking. Now, think of this as our original address space for a Class C address. In a Class C, only the last octet is host addresses. The first 3 are fixed, so you have no control over those. So in the address space, 0 would be my network, 255 would be the broadcast. And I would have 254 hosts between those two. If I borrowed the first bit, I could divide that address space up into 2 halves. Again, we must be careful because that second half, the broadcast, would be a broadcast that goes to all devices. So we use the first bit borrowed. So it's borrowed from the host portion and is added to the network portion. So it is the first bit on the left, as you see here in the red. And we have now created two equal sized groups, 0 through 127, that is the network through the broadcast, usable addresses 1 through 126. And a second group, 128, which is the network, to 255, which is the broadcast. If I were to borrow a second bit, I could now have 4 address spaces: subnet 1, subnet 2, subnet 3, and subnet 4. And as you can see, all we are doing is counting up in binary: 0, 0, 0, 1, 1, 0, and 1, 1. So now I have 4 equal sized groups of approximately 62 addresses each. The first one, 0 is the network, so 1 is the first, going to 62, which is the last, 63 being the broadcast. So now we have some smaller group, but again, each group is the same size. For one of the groups, I could borrow the third digit. I am not changing subnet 1, subnet 2, or subnet 4. Those are still 0, 0, 0, 1, and 1, 1. I am only borrowing a third bit for subnet 3, creating 3A and 3B. Notice the 1, 0 is the same in both. And I am using now a third digit to indicate which grouping it is. I could additionally borrow a fourth digit for one of those. Breaking it down even further. So each of these groups have 62 available hosts. This group goes from 128 to 159. So this has 30 available hosts. And each of these groups go from 60 to 175. And remember, the 60 is the network, 175 is the broadcast. So each of these groups would have 14 available hosts. But the mask for each one of these groups could be different. So in the same network, for subnet 1, this would be a /24 plus 2 more, /26. We would see that also in subnet 2, and subnet 3. Here in 3A, it is the original 24 and 3 more. So this would be a /27. Here I've borrowed 1 more. So the original 24 plus 4 more. So these would be a /28. Could I further divide these if I wanted to? Yes, I could borrow another bit and cut this space in half. Sometimes people refer to this as subnetting a subnet. Whereas as a company, if I go back to my General Motors, maybe I give subnet 1 to Chevrolet. And they subnet this using additional bits to East Coast, West Coast, Northern, Southern. They divide it up to make their network arrangement work for their business structure. Because the subnet mask changed, this is where the term variable length subnet masking comes from. Now we are fitting the number of hosts to match the network that they are going to, wasting the fewest addresses. Here, we take a topology. 7 subnets are required, 4 LANs and 3 WAN links. The largest number of hosts is building D with 28 hosts. If I were to use a /27 mask, that would provide me with 8 subnets, each one of 30 hosts. Could we network it that way? Yes, we could very easily. But again, the waste of addresses is not good because for future expansion, we may need those addresses. Again, this is a one size fits all. However, the point-to-point WAN links only require 2 addresses because it only has 2 ends. So we therefore waste 28 addresses on each one. So 84 unused addresses. This is applying traditional subnetting scheme, and to that scenario, it's not very efficient and is extremely wasteful. That's why we developed variable length, to avoid wasting addresses by enabling us to subnet a subnet, such as these 2 hosts. Instead of being a /27, we would make it a /30. That leaves us with 2 bits because an IPv4 address has 32. In the last 2 bits of hosts, it could be 00. It could be 0, 1, 10, or 11. This is the network address. This is the broadcast address. And these 2 are our host addresses, which is precisely what we need for a connection that only has 2 ends. So here, using their pie charts, they're showing how, using a traditional scheme, everybody had 30 hosts. The right pie chart, once we use VLSM, we take one of those sections of pi and we subnet it further to provide connections or networks only to our links that go between the routers. So when using VLSM, always begin by satisfying the host requirements of the largest subnet and continue subnetting until the host requirements of the smallest subnet are satisfied, and the resulting topology with VLSM applied. And as you can see, we're using a /30. So using VLSM subnets, the LAN and inter-router network can be addressed without unnecessarily waste, as shown in the logical topology diagram. As you get more experience with subnetting, there's many other things that you can do. When we take into account routing protocols, the number of entries in the routing table becomes critical. If you have a router with 1 million entries in the routing table, there's time wasted as the router has to go through each entry to find where to forward your data. If we could take that table and make it only 500,000, we've now increased the efficiency by 100%. So as we lay out networks, and as you become more experienced, these are some of the factors that need to be taken into account. How can we make it efficient, that we are not wasting addresses? And how can we keep the routing table as concise as possible? So we look for a structured design. The IP network planning is crucial to develop a scalable solution to an enterprise network. So to develop an IPv4 network-wide addressing scheme, you need to know how many subnets are needed, how many hosts a particular subnet requires, what devices are part of the subnet, which parts of your network use private, which use public, and many other factors. You also need to know the needs of the organization's network usage. So you must perform a network requirement study by looking at the entire network to determine how each area will be segmented. Determine how many subnets are needed and how many hosts per subnet. And you must prepare for future expansion. Determine the DHCP address pools and layer 2 VLAN pools. You must put in some logical thought before you start creating your subnets. Some of the different things that you may have. End users. Most of the end users will use DHCP, Dynamic Host Configuration Protocol, to reduce errors and burden on network support staff. IPv6 clients can obtain address information using DHCP v6 or SLAC, Stateless Address Auto Configuration. Servers and peripherals should have a predictable static IP address. And this is what we had mentioned earlier, in that once you know the block of addresses, where should these different devices be put? Servers that are accessible from the internet, they should have their own group of address, which can be NATed so that outside users can find the web server, the web page for a particular company. Any kind of the intermediary devices should be on a network for management. This would not necessarily be the network that we are using for end host devices. This could be part of a management network that manages all of our routers, switches, and other intermediary devices. And then where should the gateway be? You can make the gateway the very first address in the network, the very last network, or any address in between, as long as it is known which address is the gateway. And it is generally recommended that you have a set pattern of how addresses are allocated. You may want to say that your gateway is always the last address in the network, or always the first address in the network. When I was setting up mine, I used the very last. And because there were over 100 IP cameras, that way camera 1 could have address 1, 2 could have 2, and so on. So it became a logical way of setting things up. This concludes chapter 11. And as I said, this is probably the most important chapter. I've also provided some additional videos to show you how to configure VLSM and create an addressing scheme for networks. Using this diagram from the curriculum, I have constructed an Excel spreadsheet to show how we would configure the addressing for all of these devices. As you can see, I have set up the binary, and this is our base network without any subnetting involved. These are the networks that we need, and we will use this area to develop what bits will be network and what bits will be hosts. I have constructed the Excel table so that it will automatically calculate the binary and add it to the end of our addresses. This I had showed in a previous video. I have put a line showing the number of hosts that would be available for the number of bits that we have borrowed. First, if I am going to start out, I will now fill in my chart first with the base, and then we will construct it to be able to provide 28 hosts. The network address is always all zeros. The first usable address would be all zeros and a 1. The last usable address would be all 1s and a 0. The broadcast would be all 1s. And at this time, the subnet mask is all zeros. That is where we will start. First, let's move here and determine, in order to get 28 hosts, these bits must be host bits. That would give us 32 combinations, 30 actual hosts. Because I only need 28, 30 would be acceptable. That means that these bits will be our network / subnet bits. As we can see here, 3 bits are borrowed. I will put a line down to show that that is where the subnet mask should be. And I will make these bits red to indicate that those are my network subnet bits. Now the network subnet bits must be all the same. So if the top row is all zeros, that means that all the rows below it, before we get to the subnet mask, must be the same. So if the top row is all zeros, all the ones below it must be zeros. The subnet mask, to indicate that we have borrowed those 3, those will be 1s. Because this is a class C, the default subnet mask is 24. I'm only working in the last octet. So I have 24 bits, and I have borrowed these 3 additional bits, giving us the 255, 255, 255, 224. That would work out to be a slash slash 27. A slash 27 because I have the original 24 and 3 additional. So we can see our network addresses. 0 is the network. 1 through 30 are usable host addresses. 31 is the broadcast, and the subnet mask is 255, 255, 255, 224. Now, to show you the most efficient way to do this from one network to another, I will copy what I have for building D, paste it down below. We will be changing this. The next largest is building A, 25 hosts. So again, in order to get 25, the last 5 bits will be hosts, and the first 3 will be network / subnets. So you can see this 2 will end up being a slash 27 because I have borrowed the same number of bits, 24 bits plus 3 additional. Now the main thing to remember is that the subnet bits cannot be the same in one subnet as they are in the next. So we must count up in binary. We're starting with 0, 0, 0. If I add 1, that will make sure my addresses do not overlap. The mask is staying the same because we needed the same number of bits. You can see how this subnet, the broadcast ends at 31, the next network begins at 32. You can never have overlapping networks. Because this is where I left off, I will copy that to be my next starting point. Building B needs 16 hosts. But if I said here and just went those hosts, I would have 16 combinations, but because of the network and the broadcast, I would only have 14 usable. So this must also be a host bit. Just as before, the first 3 bits will be network subnet bits. So the mask will stay the same at a /27. This is where we left off with building A. I cannot reuse those addresses in another network. So in order to make sure that they do not overlap, I must count up by 1 in binary. Here are my bits, 001, or 1 in binary. What comes after 1? 2. 2 in binary would be 0, 1, 0. And that's what I will put the entire way down. The subnet mask has not changed because it indicates how many bits have been borrowed. So we can see we ended with 63 here on building A, and we are starting now with 64 on building B. Because this is where I left off, I will copy that to the next group for building C. Building C needs only 10 hosts. In order to get 10 hosts, I only need 4 host bits. That gives me 16 combinations, 14 that are usable. So now the first 4 bits are network subnet bits. So now for building C, I must move my mask line. So I will take it out of there and move it over 1 place. Why 1 place? As we determined earlier, the first 4 are my network subnet, which means I am borrowing 1 more bit. So this has now become a network subnet bit. And I will change those to red to indicate that. Now you'll notice here, I still have the 0, the 1, and the 0. Technically, before moving the mask line, this is what should have been done. And I will go back to where it was. Before moving the mask line, the first thing that you should do is count up by 1. So I'm at 0, 1, 0, or 2. I will count that up to 3. Now that I have guaranteed my addresses will not overlap, I will move the mask line. And I will include the one additional bit that we needed to borrow. Remember, in the subnet mask, we must have a 1 to indicate that that bit is part of the subnet. And the top row has to be the same all the way down. So I have to change that bit that I borrowed to reflect the 0 at the top all the way down. My subnet bits always have to be the same. Now, because I have borrowed 4 more bits, the original 24 plus 4 gives us a subnet mask of a /28. And you can see how building B ended at 95. We are now starting at 96. We are ending at 111. The next is for the connection between router 1 to 2. This only requires 2 hosts. To get 2 hosts, all I need is 2 bits. That gives me 4 combinations. So all the rest become network subnet bits. So 1, 2, 3, 4, 5, 6 bits from the left now become network bits. I will copy where I left off. Before moving the mask, I will count up. I ended with 110 or 6. I will now change that to 111 or 7. I can now move my subnet mask. So I will take it out of where it was, and recall there's only 2 bits that are hosts. So we will move the subnet mask over 2 additional bits. And place the mask line. These 2 bits have become part of the subnet. Remember, the subnet mask must always be 1s through the subnet bits. And the top row must be reflected all the way down. So you can see now we ended at 111, we start at 112. Because I only have 2 bits left, 32 is my total, minus the 2, it is a /30. And this you'll find very common for all serial connections. My next connection is from R2 to R3. Again, 2 hosts. So just like in the connection from R1 to 2, the first 6 were network subnet bits, and the last 2 were host. Because this is where I ended, I will copy that down. I cannot use the same subnet again, so I must count up. I ended with 11100. I now must go count up by 1, so 00 becomes 01. I have not changed the subnet mask at all, so it is still a /30. And my addresses are configured. One of the things you may notice about the serial links, or when we get down to only a 2 connection, the addresses are consecutive: 112, 113, 114, 115, 116, 117, 118, 119. We can pretty much guess where the next 4 are going to be. Again, this only needs 2 hosts. So 2 host bits will give us 4 combinations, 2 that we can actually use. Just as before, the first 6 bits are all used for the subnet. Because this is where I left off, I will copy that down. Now I've already used the 116, obviously, so I must count up. So from 01 in binary, the next would be 10. And it falls right into our pattern: 19, 20, 21, 22, 23. And again, because the subnet mask has not changed, it is still a /30. We now have all the addresses that we need to configure this network. You might want to build this in Packet Tracer using these addresses and make sure that it works. This will conclude the video on Chapter 11.